Yes.
Can we start now?
Yes, okay.
Okay. Good morning to one and all. Welcome to the webinar series, Lecture 2 on some distance-related problems in graph theory, organized by the Research Department of Mathematics, St. Mary's College, Thrissur, in connection with the Platinum Jubilee celebrations of the college. Our resource person today is Dr. Pravas K, Assistant Professor, Department of Mathematics, KKTM Government College, Pullot. He did his PhD on the topic, Studies on the root graphs of some graph operators from Cochin University of Science and Technology. On behalf of Department of Mathematics, St. Mary's College, Thrissur, I welcome you, sir, to this webinar. I welcome Principal Dr. Sister Maggie Jose in her absence, and Head of the Department, Dr. Parvati KS, and all dear participants to this webinar. Next, I invite the resource person, Pravas sir, to handle the session.
Hello, everyone. So, good morning. And first, let me thank St. Mary's College for organizing this program and calling me to deliver this presentation on this topic. Now, I think I should start with presenting my screen. Just a second. So, is it visible now?
Yes, sir.
Yes. Okay. Yes. So the topic is some distance-related problems in graph theory. So I think many of the participants are PG students. So I will explain the first few results from the very basic concepts of the graph theory, and then go to other higher things. So this will be the outline of my presentation. So first I will be talking about what is mean by meaning of facility location and what is a facility location problem. Then I will be making more on these types of problems called the median problems and its special cases, and finally end up with the simultaneous embedding problems. Now, many of you already know what is graph theory. Okay, it's a mathematical structures known as graphs are used to model pairwise relations, and the study of graphs. Okay, that is called graphs, and the study of graphs is the branch of mathematics which is called the graph theory, and originated in 18th century. Now, before going to the next slide, let me draw a graph. Okay. So let us consider some objects. Okay. So here usually objects or people or computer or whatever be the objects under consideration are represented using dots or small circles, and we call these as vertices. So objects can be anything, or vertices can be anything. Now I already mentioned that the pairwise relations between these objects are under, that is what we are investigating. And when we have some relation between these vertices, we call it as the vertices. So if it is V, U, W, X, Z, usually we represent it using the small letters. And when V and U have a pairwise relation or some connection, if they are computer, if there is some connection between them, if they are people, if there is some relation, any kind of relation between them, then we usually denote with a line segment connecting that to objects or vertices or people or computers, whatever. Now, when you consider the notations, G is the standard notation of a graph, and or any capital letters we usually put as a notation. And V of G is the vertex sets denote the vertex set of G. So here you can see that V U W X Z forms the vertex set of this graph. Okay, and E of G is the edge set. So here edge set means these relations usually denoted with ordered pairs. So here need not be ordered pair. So here VU is a pair, WX is another pair, and so on. Now, what is degree of V? Degree of V is the number of adjacencies, okay, of a particular vertex. If we choose it as V, then here only one vertex is adjacent to this vertex, or here it is now, sorry, it is having two vertices adjacent to V. So the degree of V is 2 here. And so this is a notation for degree of V. And what is Pn? Pn is the path of length. Path means a set of consecutive non-repeating vertices. For example, here you can see that from U, V, X, W. Okay, it's a path. Now I told you path of length n. What do you mean by length? Length is the number of edges in that involved in that sequence of vertices. For here, here you can see that from starting from U to V, there is only one edge, so it is counted as 1. And V to X, it is again 1, means there is only edge, only one edge is there. And XW is again, there is an edge here. So total number of edges from U to W is 3. So UW is a path of length 3. Okay. Now, what is DG of UV? DG of UV is the distance between U and V. Okay, so if I consider, say, UW is another edge, UW is also an edge here, then what is DUW? Okay, now distance means it is the length of the shortest path between that two vertices. Okay, so here you can see that already you have a path from U to W of length 3. So you have a path here of length 3. And if you consider UW as another path, okay, UW is also another path. So you can see that this has length 1. So the shortest of these two is, here it has 3 and here it has 1. So the shortest is 1. Okay, so the shortest distance between U and W, or sorry, the shortest length, or the length of the shortest path between U and W is denoted with this DG of UV, and which we call as the distance between the vertices U and V. Okay, now what do you mean by facility location? Okay, so let us have some property, or let capital P be some property which we define using graph theoretical terminologies or anything other than that, or let it be some desired property, and let small v be a vertex in that graph with that property. Okay, then we can call that vertex as a facility location. Okay, so for example, let us assume that P is the property of having say degree 4. Okay, so degree 4 is a property. Then all vertices in that graph having vertex degree 4 is going to be a facility location according to that problem. Okay, but is there any application for a vertex of degree 4 that we don't know? Means that has to be defined by the person who has defined that desired property. Okay, now or we can call it by different names also. For example, when we consider the centrality concepts, okay, the facility locations are also called or known with different names. So I will be going to that slide now. Okay, so here I have defined some properties. Not me. The properties are that the importance of a room. Okay. Now, what is the corresponding property that we should have? So how to claim that a room is important in a building? Or if you go to the next problem, how influential a person is in a social network. Okay, so how to define a property for that person so that we can call him as influential. Okay, now the third one is how well used a road is in a transportation network. So when you can call a road is uh, well used or very important in a transportation network. Okay, and the usual question, how important a web page is. Okay, now how to identify the property of the corresponding properties of these types of questions and how to give a solution. Okay, and that is my next slide. So the first one, the facility location, which we call as the centrality, degree centrality. The node with the highest degree, if we consider when considering the persons who have more influence on others, no, the node with the highest degree is considered to be a property. Okay, and when it is made a property, you can see that our second problem, maybe yes, we can identify a person with a who is influential in a social network. So for example, here in these three pictures, you can see that this person has the highest degree. Okay, because he is connected with these many people, and so this person uh, is more influential according to this theory. Okay, now for example, if you consider the gossip network, that person, central actor more likely to hear a gossip, right? Because he have more connections with the more other people of the same industry. Now let us consider another problem, another property. So closeness is the property that here I am defining. The closeness is a measure of the degree to which an individual is near all other individuals in a network. Okay, so we have a mathematical expression for that also. So it is calculated as a reciprocal of the sum of the length of the shortest paths between the node and all other nodes in that graph. Now, hope it is clear. So you have to, if V is a vertex or U is a vertex, you have to calculate the distance from U to all other vertices and take the sum. Okay, so V in say capital V, and you take the reciprocal of that. Okay, now this is how the closeness centrality is measured, and in that, if a vertex is having that minimum or maximum, we define two extremes of this closeness centrality. So it is a measure of the degree to which an individual is near all other individuals in a network. Okay, now one of the point that we can notice that in a biological network, a protein with a high closeness will be easily central to the regulation of other proteins. Okay, now going to another type of property and the facility location, and this one is the betweenness centrality. Okay, so the betweenness centrality quantifies the number of times a node acts as a bridge along the shortest path between two other nodes. Okay, so we already discussed a question or how important or how well used a road is. Okay, so here is the answer for that. So in telecommunications network, a node with a higher betweenness centrality would have more control over the network because more information will pass through that node. So in order to, if we identify that node with the more betweenness centrality, then you have to give priority to that particular node, because if that particular node fails, then it will affect the entire network other than any other failure of some other nodes. Okay, now here you can see that this person, okay, and if you lose this person, then you can see that these two networks, that is these two group of people, would be disconnected. So this collection of people and this collection of people are connected with this particular person, and if this person uh, don't respond or don't work properly, you can see that the entire connection or entire network fails. Okay. Now I have included this part, this facility location concepts, in order to show you that there are different properties that we can define different properties and define different facility locations in that way. But I am not interested, or my agenda is not to discuss these types of facility locations. I want to discuss on the facility locations related to the distance concept. Of course, the previous one is related to the distance concepts in graph theory. Now, so if you want to note or read more on this, you can see these types of books which are available in the market. The social networking, analyzing social networks, and some other books are also there. You may put a screenshot now and let us search on this. Okay. Now the book I want to mention for the topic that we have today is the distance in graphs. Okay. Because I want to mention on some distance related problems. So I can see that all the definitions, or most of the definitions that I am going to present today is from this book, or very basic concepts are from this book. So this is also available in the market. Now let me go to the next set of facility location problems. So the problem here is that what is the optimal location, okay, of a hospital such that the worst case response time of an ambulance is minimal. Now we know that the hospitals are playing one important role in the society. It's a era of that COVID and other related issues. So where should we place a hospital? That is one of the important question. Okay, we already placed many hospitals, but sometimes we think about whether it was better. It would have been better if there was a hospital somewhere nearby. We might have some that imaginary location in our neighborhood. Okay, so what should be the optimal location of a hospital such that the worst case response time of an ambulance is minimal? So I will be coming to the answer of this problem later. Now another question. So this will be a different question. What is the optimal location of a shop? And the condition is that if customers buy at the nearest shop and there will be a competitor placing its shop after we have placed ours. Okay. So we should find a location and open a shop, and it should be optimal in a such a way that if another shop is opened after placing our shop, our location should be the optimal one. Okay. Now the third problem is, what is the optimal location of a network server? So this is also very important in these days, so that the average time to respond to other computers in the network is minimal. Okay. So how to place a computer server or network server? Okay. Now I will be going to the answers of this problem one by one. So the first one, where should be the location of a hospital? Now here is the first property that we have. A vertex V is called a central vertex if E of V is equal to RADG. What is E of V and what is RADG? Yes, here you can see that E of V is the maximum of distance between V to all other vertices U in that graph. Okay. So before going to the next word, let me compute E of V for this particular vertex. So let us calculate E of V of this vertex. So let us calculate the distance between these two other vertices. So distance from this vertex to this vertex, or distance from this vertex to this vertex is 0, we know. Distance from this vertex to this vertex is, now it is 1, because there is only one edge between them, so it is 1. And distance to this vertex is, or the better way is to write on that particular vertex. Okay. So this is distance to this vertex is 1. This is also 1. This is also 1. And this is also 1. Distance from this vertex to this vertex, you can see that 1, 2, 3 is the distance, but is a path of length 3. And there is also 1, 2, a path of length 2 is there. So it should be 2. So 2 is the minimum length of the shortest path between 3 and these two vertices. And distance to this vertex is 1 more, that is 3. Okay, so what is the maximum of all these possible distances from this particular vertex? It is 3. So that is why it is denoted with the 3. Okay, now I have calculated, so this is called the eccentricity. E of v is the eccentricity of the graph, and it is 3 now. Now what is RAD of G? RAD of G is the radius of G. Okay, so this is a numerical value, and this value is the minimum of all these values. So here you can see that 4 is the eccentricity, 3 is the eccentricity, 2 is the eccentricity of these vertices, and 4 is eccentricity, and the minimum here is 2. Okay, so here you can see that the RAD, that is radius of G, is 2 now. Okay, now let us see what you mean by a central vertex. A central vertex is a vertex whose eccentricity and radius of G matches. Okay, so here you can see that there is only one vertex with the eccentricity 2, right? So which means that this, according to this definition, we call this as the central vertex. Now let us think about another problem. What is the minimum or maximum distance that each vertex has to travel to this particular vertex? What is the maximum distance for each vertex, or from each vertex, so that we can reach to this particular vertex? So here you can see that if you take any vertex in that graph, the maximum distance, or if you consider distance as hours or minutes or whatever maybe, or kilometers, the maximum distance that you need to reach from one particular vertex, maybe from here or here, from any vertex to this particular vertex, is 2. So which means that if you place a hospital here, okay, if you place a hospital here, then it is possible for each of the vertices in this graph, or each of the objects in this graph, or each of the other cities or homes in this graph, to reach this particular vertex in 2 hours or 2 minutes, or whatever be the unit that I have defined. Okay, so you can see that this should be the location of a hospital. So the central vertex plays that important role of finding an optimal location for a hospital. Okay, now there is one more definition. Let me go through that also. The graph induced by the set of central vertices of G is called the center. So you can see that here, this is the only vertex with the eccentricity is equal to 2. Okay, so this graph induces this graph, that is the graph with only this particular vertex is the center of this graph. Okay, now if radius of G is equal to diameter of G, then this graph is called a self-centered vertex, self-centered graph. For example, if you consider this graph, okay, maybe this also may work. Yes, this graph, you can see that the eccentricity of each and every vertex will be okay, not this one, 2, right? So here you can see that the eccentricity of each of the vertices is 2, which means that this is a self-centered vertex. So the minimum value is 2, the maximum value is also 2. Okay, so this graph is called a self-centered vertex. Now what happens if eccentricity is equal to the diameter of G? Diameter means it is the maximum value of the eccentricity, then it is called a peripheral vertex. Okay, and if we identify the set of all peripheral vertices G in G and take the induced graph, then we call it as the periphery of G. Now let us solve the next problem. So again my agenda is to give more on the third problem. So I will be just mentioning the solution of the second problem and going to the third one. So here I define the centroid of a graph. Okay, the centroid is a before that we have a tree, capital T. So tree means there is no closed cycle in this graph. Cycle means it's closed. There is no cycle in this graph, and it also should be connected. And if you remove this some particular vertex, so if let me remove this particular vertex, then you can see that this is one particular vertex that is isolated now. This is another vertex that is isolated now, and this is another collection that is disconnected now. Okay, now let us count each of the collection, the number of vertices in each of the collection. So here you can see that this blue has only one vertex. Okay, you have three disconnected parts, and here we have only one vertex, and here you can have only one vertex. And in this collection, if you delete this particular vertex, you can have three collections, and this collection you can see that there are 12 vertices. Okay, yes, so I can denote, or I can call, this is the branch weight of this particular vertex. Okay, so the branch weight of a vertex is the maximum number of edges in a subtree, okay, with u as an endpoint. So which means that equivalently, if you delete this, what is the maximum size of a disconnected component? Okay, now what do you mean by branch weight centroid? So let us calculate the branch weight of each of these vertices. So you can see that this will be 9, this will be 12, this will be 6, and this will be 11. And you can see that this vertex has the minimum branch weight in this particular structure. Okay, so I can call this as the centroid of this graph. Okay, now if you search exactly the same sentence in internet, the second question, then you can see that the centroid is going to be the answer to this problem. So you'll be directed to the page by Peter J. Slater, and you can see that the exact question is there, and the corresponding answer explained using the centroid of the graph for a tree. Okay, now we have the third question. What should be the location of a server? Okay, here there are three rotations that we want to identify. So the first one is the status of a vertex. Okay, so what is the status of vertex? A status of vertex S of V is the summation of all the distance from that particular vertex to all other vertices. So you can be any other vertex in the graph. For example, here if you calculate, you can see that the distance to this vertex is 1. Okay, and distance to this vertex is 1. This is also 1. This is also 1. And distance to this vertex is 2. And distance to this vertex is 2 from this particular vertex. Okay, so if you take the sum, you can see that it is 8. So this is the status of this vertex. So 8 is the status of the vertex. Similarly, if I calculate all other status of these vertices, you will be getting numbers like this. Now, this is what the definition of a status. And if you choose the minimum of this or the vertices with the minimum status, so let us choose the vertices with the minimum. So I have already given a green color to this. So there are two green colored vertices, and these vertices are called the median vertices. Okay, the median vertices in that graph. And if you consider the subgraph induced by this collection of vertices, for example, here only two vertices, not for example, in this example, the only two vertices are there with the 8. So if I choose the all possible edges and vertices, all possible edges between that vertices. You can see that an induced graph is formed, and we have the subgraph induced by the median vertices, and this graph is the median of this graph. Okay, so obtained by these two particular vertices. Now, another concept is that how to what is the meaning of self-centered and self-median graphs. So it is very quickly I can cover all these topics. So a graph with the center and the graph itself matches, then you can call it as the self-centered graph. Okay, and when you can it as the self-median graph. So here it means that all vertices have equal degree, equal eccentricity. So E of V is the same for all vertices in this graph. Now, what is the meaning of self-median? Self-median is the term when we can see that the status of any vertex is in the graph matches. That means are the same. Okay, then we can call that graph as a self-median graph. So here 3 examples are given. So here this is the collection of all anti-median vertices. I usually put red color to anti-median vertices and green to median vertices. So this is a graph with both the median and anti-median graphs are disconnected. Okay, so if you take the induced subgraph, you can see that these are disconnected. This forms a disconnected graph, and here you can see that all of them are green, which means that yes, all of them have the same status and the minimum one automatically, which means that this is a self-median graph. Okay, now the last one also, this is also a self-median graph. Now this is also a famous graph. I think it is better to take a screenshot and search for this graph, and you consider this as an assignment to yourself. Now if you consider these two graphs, then you can see that all these two graphs are again self-centered. Okay, now this is also self-centered. I think yes, this is also self-centered. Means if you calculate the eccentricity of each vertex in this graph, you can see that the eccentricity is 2. Okay, so all these graphs are self-centered. Now here another problem comes. Before going to a few other slides, I am going to show you one of the problem that we face here. How can we calculate the status of each of these vertices in some real time? Okay, which means you can see that in order to find a status of some particular vertex, so let me take this vertex, you have to find out the distance from this particular vertex to each of the other vertices and take this up, then only you get the status of this particular vertex. Okay, now how to find the status of this vertex? Once again you have to find out the distance between this vertex and all other vertices again, and distance means you have to find the length of the shortest path between the two vertices. For example, if you consider this and this, what is the shortest length? That is 3. Okay, here it is 3. How I calculated that? Okay, it is possible to I have already observed that. Anyway, it is 3. Now here you need to calculate the distance between the distance from this vertex to all other vertices and take the sum. So how to identify the distance from a vertex to all other vertices, or is it possible to identify the distance from status of that vertex in very short time? Okay, there is no meaning for a short time or the opposite to that, but I will show you one of the algorithm that we use that. So let me go to another problem. This is one of the famous graph. I think we already know that. Someone can comment if possible. What is the name of this graph? Now, how to identify the distance from this particular vertex to all other vertices? What is the step-by-step method that we use? Or step-by-step method means we have to make it as or call it as an algorithm. So what is there any algorithm to identify the distance between this vertex and all other vertices? Okay. Now the method is very clear and it is called the BFS. Okay. So we are going to perform a search in this graph. Okay. Using which we can identify all the possible distance from this particular vertex to the other vertices. This is the breadth first search. Okay. The full form of this. Now how to do that? First we identify, for example, some particular vertex, maybe this vertex, and let us identify all vertices adjacent to this particular vertex one by one. Okay. So the first step is you have to start from one particular vertex and identify all vertices adjacent to this one by one. Okay, not together or everything together. For example, let me take 4 as one of the vertex. Okay, and let me take this to one end so that it is easy to identify. Okay, so 4. So this is the first vertex that we have. Let me write it as 5 is the starting vertex. 4 is the next vertex we have identified. Then I have from 5. This is also a vertex adjacent to that. So I have kept it here. So 10 is the next vertex. And let me take this. It's another possibility. Yes. So 1 is here. Right. Now I have completed or I have searched all possible adjacencies of this particular 5. So I have completed the first vertex 5 here, means in our search, in my search. Now let me go to the second vertex in this collection. So it is 4. Now from 4 you have to identify all possible adjacencies that is not already appeared in this collection. Okay, so we can see that 4, 10, 1, 5, 4, 10, 1 are already appeared in this collection or in this ordered list. So here from 4 you can see that what is the adjacency, possible adjacencies? 5. It is 5. I cannot count 5 because 5 already appeared in this ordered collection. And here you can see that 9 is one of that vertex, and 4 is another possibility. And is there anything else? No, I have covered all possible adjacencies from 4 to other vertices not already included in the ordered list that we have taken. Now I have completed with the 4. Now let me take 10. So starting from 10, let us consider the all possible adjacencies. So here it is 8. Now here this is also possible. Yeah. So 7 is there. Now from 10 I have completed all these things. Then from 1 I can see that, yeah, 6 is one possibility and 2 is one possibility. Okay. Now in this way, if you search your graph in this way, then it is possible to see that possible to identify the distance between this particular vertex to all other vertices at once. How? Because I can see that here I call this as a layer of distance 0 from 5, means all vertices in this layer are at a distance 5. Sorry, at a distance 0 from this vertex. Now if I consider this as another layer, you can see that all vertices in this layer are at a distance 1 from. So the distance from this vertex to this collection is 1. Okay. Now there is one more layer. Okay, there is one more layer available, which means that the distance from 5 to all vertices in this layer is 2. Okay. Now I can simply ask many questions to you. What is the eccentricity of this graph? What is the eccentricity of graph? Here you can see that 2 is the maximum possible distance. So which means that it is 2. I asked not eccentricity of the graph, eccentricity of this vertex. Say V5. Okay, sorry. Now what is the sorry? Yes. What is the status of this particular vertex? Now it is easy to calculate the status. I already defined the status as sum of the distance between V to all other vertices, where you can be any other vertex in the graph. So here you can see that there is only one vertex with 0 degree, sorry, at a distance 0. So it is 1 into 0 plus. Now there are 3 vertices at a distance 1. So it is 3 vertices at a distance 1 plus there are I think 1, 2. Is there any vertex below that? No. So it is 3, 4, 5, 6. Okay. Yes, it is 6 vertices at a distance 2. Okay. Now, if you now it is possible to easily calculate the status of this vertex. 3 plus, right, 12, right? It is 50. Now, in this way, if I perform a BFS, that is the breadth first search algorithm, using this algorithm, it is possible to find out the distance. Now you can see that it is, you can identify the you can perform this algorithm in some log n steps. If I take some n as the number of vertices in the graph, it is possible to identify or perform this in around log n steps. Now let me come back to my slides. There is one more algorithm, and you need to search that in Google search. So there is BFS. So BFS is, I already mentioned, it is breadth first search, and there is one more word, DFS. Now this is the second assignment to you, to find out what is D, and this is equally important when we perform the search algorithms. Now another thing you can see is that if you start with from this vertex, and if it is possible to reach all the vertices in the graph using BFS. Okay, so you can see that here we have started from this vertex, and we could perform this search so that we could reach all the vertices in that graph, which means that this graph is connected. Okay, so in order to identify whether a graph connected, you simply put a BFS from any vertex in that graph. Okay, so there are many applications to this BFS, and also this DFS, and I'm stopping that problem here, and if some undo option is performing. Okay. Yes. Now I will show you how this algorithm works in just a few seconds. So once again, let me start with the same graph, and I have chosen this, and let me perform the breadth first search, and we need to select one of the starting node. I have taken this, and you can see that, yes, this is the first adjacency, this is the second adjacency, this is the third adjacency. You can see that they are marked in red color. So this is the first identified vertex. Now from the first identified vertex, this is the first adjacency, second adjacency, now and so on. And if I play that, you can see that all the graphs can be formed in this way, and the nodes added to this queue is, we already saw that 5, 4, 1, 10, 3, 9, 6, 2, 7, 8 is going to be the search or the result of the ordered list that we have obtained using this BFS. Now I am going back to this problem. Okay, now already you know what is a median vertex, anti-median vertex. Okay, and what do you mean by self median? Now this concept, if you want to know more about this concept, you can refer this paper. So this median concept was introduced in 1869 by C. Jordan, and he already in that paper itself, he have proved that the median of trees is either K1 or K2. Okay, K1 means the single vertex, or K2 means the connected two vertices. Okay, now the anti-median concept is discussed in this paper by Black and Sislow in 1983, and there is one more paper, and all you can see later. Maybe you may take a screenshot now. Now, the another problem related to these concepts is that, can you have a graph? Okay, for example, can you have a graph, and can you find out another graph says that this graph is the center of some connected graph? Okay, so given you a graph, say H, so I have given you H. So can you find out a graph G such that the center of the graph is the graph with us, that is H. Now you can see that this Hernimi already proved that it is possible to construct such a graph. Now the proof is also very, you can easily find out the proof. For example, let H be any graph. So this is a structure that shows a graph is here, some arbitrary graph is here. And let us introduce some two vertices, for example, V1, U1 here and V2, U2 here. Now you make all possible adjacencies between this vertex and this graph, and also this vertex and this graph. Now you make another adjacency like this and another adjacency like this. Then you can see that all the vertices in this graph, okay, is now having eccentricity of V is equal to 2. So if V is any vertex in the graph, then you can see that eccentricity of V is equal to 2. Now if you take this vertex, you can see that the eccentricity of this V2 is equal to 3, because in order to reach U1, you need to travel from here to here, 1 step, 2 step, and 3 step. Okay. So, and similarly, you can see that the eccentricity is 4 here, 3 here, and 4 here. So you can see that if you make a construction like this, you can have a graph as a center of another graph. Okay. Now the same question appears in median also. Now there is another problem related with that. You can see that not every graph is the periphery or anti-center of some graph. Okay, but there is a condition that it can be possibly periphery of some connected graph if and only if no vertex of G has eccentricity 1 and or all vertices of G have eccentricity 1. Okay, so if you have this condition, then you can see that that graph can be a periphery of some another graph. Now this is the Peterson graph. Okay, that was our previous assignment to name that graph. Anyway, you can see that if I add 3 more vertices, here I have added 3 more vertices to this Peterson graph, and I can see that this is now a center of this newly generated graph. So what is the meaning of this? Yes, it is this 4, the value 4 is not optimal in the previous construction. Okay, so that is not a optimal value. However, that is an optimal construction. Okay, the value 4 is not optimal, but that is an optimal construction, because whatever be the graph, you can perform that. But you don't need 4 vertices each time to have a graph with the prescribed center. Okay. Now going to the next slide. So I call the following problem as median problem. We already what we have seen in the center is there, and the problem is that you have given a graph H, and the problem of finding a graph G such that the median of that graph is the given graph is referred to as the median problem. Okay. So you have say I am going to give you some structure. Say let it be like this, and now I want all these vertices, all these structures to be as the computers or vertices with the property that they are the servers of some another particular network connection. Okay, I think I don't know whether I have clearly mentioned that problem. So here you need to have this graph as the median of that particular graph. Okay, so the significance of the problem I have written there, that the median vertices, you know, already I mentioned that it is they are with the minimum status or minimum average distance. So in network theory, this is significant as it is related to the optimization problems involving the placement of network servers. Okay, and we know that this is the core of the entire network. So when we have a very large interconnection network, it is very important, and therefore the problem is important. If you have given a structure, can you find out a network with this structure as the median? Okay, now this problem already have a solution. That is, the P.J. Slater itself in 1980 constructed a graph with a given graph as the median using the cube of the number of vertices cube vertices as the total number of vertices required to construct the new graph. And Miller in 1983 improved this result to 2 times vertex set of G. Okay, so you have given 10 vertices. He promises to give another graph in some 20 vertices, so that this graph is the median of that graph. Okay, then later on, G.R.T. Henry improved this result to 2 times vertex set of G minus delta. Delta means the minimum degree of the graph in the graph plus 1. Okay, then similarly, the result for anti-median also exists. In the paper I already mentioned, the Bailey-Kansas law proved that any graph G is the anti-median of some connected graph. Okay, so you can see the references here. Now we can see that this is the solutions are general, but we have some limitations to the general solutions. The thing is that the median constructions for general graphs cannot be directly applied to many networks. Okay, why? Because the underlying graph of many graph networks belong to different classes of graphs. Okay, so let me introduce you some other different graph classes. The first one is the Ptolemaic graphs. Okay, and already we have a solution by these researchers. That is, you given you a Ptolemaic graph, or yes or no. They means an answer means it can be yes or no. Okay, given you a Ptolemaic graph, whether it is possible to embed that graph. Embed means make it as a subgraph. Okay, embed as a embed that graph as a subgraph of another graph with the given graph as the median. Okay, now another one is the distance hereditary graphs. I will be giving the definition of these graph classes after a few slides. Then this result is already discussed by Jija Chang et al. And another result from S.B. Rao and Dr. Vijay Kumar on co-graphs. And on k-party graphs, there is another result, which means that given any k-party graph, you can have another k-party graph such that this given graph has the given graph is the median of the newly constructed graph. And also there is one more construction for symmetric biparty graphs. So I'll be explaining all these concepts one by one. Now, what is distance hereditary? So a graph is distance hereditary if for any induced subgraph, the distance between any induced subgraph H, the distance between any two vertices U and V in that subgraph H is the same as the distance between the same vertices in the original graph. Okay, now you can see that this a distance hereditary graph can be easily identified as some HDG free graph. Okay, so this is a characterization for distance hereditary graph. So there should not be a hole, house, or domino. Okay, domino maybe all PG students might have know, and germ. Okay, so there are 4 names I already mentioned. So you go through the internet and search for the words. So there is a hole, house, okay, house, hole, domino, and germ. Okay, if it is possible to draw a graph without these graphs, then you can see that is going to be a distance hereditary graph. Okay, now caudal graph. A graph is caudal if every cycle of length at least 4 has an edge which we call as the chord joining 2 non-adjacent vertices of the cycle. Okay, so which means that whenever you have a cycle of length 4 or higher, you can always find a chord. Okay, so that is what a caudal graph. And a graph is Ptolemaic, already mentioned that if it is both distance hereditary and caudal. So if you take the intersection of this, okay, if you take the intersection of this, and you can see that it is a Ptolemaic graph, right? Now the result of Ptolemaic graph says that the median of Ptolemaic graph is complete. Okay, which means that if you have a Ptolemaic graph which is not complete, it is not possible to create another graph with this graph as the median. Okay, so that is why I already mentioned that the answer, the research means it can be a yes answer or a no answer to a particular question. So both we can consider. If you have a correct proof for your result, then you can see that both are valid researches, and you can claim that. Now, another thing is that every connected component of the subgraph induced by the anti-median of a Ptolemy graph is complete. So which means that if you have a Ptolemy graph other than a complete graph, then you cannot have a graph whose median is this particular Ptolemy graph. Okay. Now another concept is two trees. So let me define what you mean by a two tree. A two tree is a graph formed by a starting with a K3. So K3 means the triangle. This is what a K3 is, and then repeatedly adding vertices in such a way that each added vertex U has exactly two neighbors V and W, such that UVW forms a K3. So which means that you can make another two tree by introducing a new vertex. For example, let me add a new vertex. What is the condition? The condition is that you have to make exactly, you need to find out exactly two adjacent neighbors in this graph. Okay. For example, if I select this and this, then you can see that this is another true tree. Okay. And that is how it is obtained. Now I can improve this. For example, let me add one more vertex, and if I add say these two adjacent vertices, these two vertices are adjacent, so this is another two tree. Okay. Now this is not a two tree. Okay, let me make it with another color. So if I have a new vertex and I have made adjacencies with two more vertices, but they are not adjacent. Okay, so this is not a two tree according to this definition. Now the statement related with this is that the median of two tree is isomorphic K1, K2, or K3. So this is exactly the same result that we have, similar to the result that we have mentioned with the Ptolemy graphs. So you cannot have a median other than K1, K2, or K3 when it is a two tree. Okay. Now I want to so I already hided that notification here, whether I am presenting or not. So if there is any problem, please mention it. I have removed that column here, that box here. Okay. Now another thing is that cographs. Okay, the cographs is the complement reducible graphs. Okay, that is they can be recursively generated in the following way. That is, if you start with K1 as a cograph, then if G is a cograph, then its complement is also a cograph. And if we have two cographs, that is G and H are cographs, then the disjoint union is going to be a cograph. Okay. So if you go through the definitions and perform some calculations, it is not difficult, however not easy also. You can see that a graph is cograph if and only if it does not have a path P4 as the introduced subgraph. So which means that if you draw a graph without a graph like this, okay, then you can see that you can have a cograph. Now, what are the related problems with the cographs? The problems are, or the results that already exist in the literature are: the median graph of a connected cograph is a subgraph induced by the vertices of maximum degree. So this is one of the results. So in order to find out a median of a cograph, you don't need to calculate the status. You just need to calculate the degree of that vertex. Okay. So if you have a graph and if you find out the vertices with the maximum degree, then you can see that it is possible to identify the median graph. Okay. So that is one of the important result. So if you see that you have given a very large graph, and if you already know that it is a cograph, then there is no need to perform a distance calculating algorithm or whatever be the process you have. you just need to identify the degree of that vertex and identify whether it is a median vertex or not by performing it for all other vertices. Now another thing is that if M1 and M2 are median graphs of two graphs G1 and G2 respectively, then you can see that M1 union M2 is also the median graph of a connected graph. Okay, so it is possible to have M1 union M2 as the median of another graph, another connected graph. Okay, now if there is an Eulerian cograph, okay, so this is another word that you need to search if you don't know. Very little time that we have to explain this, or you can see some graphs that you can draw without taking your hands, then that are called the Eulerian graphs. So if there is an Eulerian cograph of G of order P such that M of G is equal to H, that is the median of G is H, then there exists an Eulerian cograph G of even order such that M of G is equal to H. Another result is that every cograph G is the median graph of some connected Eulerian cograph. So which means that you can have any cograph as the median of another cograph. Okay, and that cograph has the additional properties, that property you can also have an additional property, the Eulerian property. Okay, now yes, the continuation of the results in the same paper. Any cograph is the anti-median graph of the connected Eulerian cograph G of even order. So you can have a graph of even order also. And if G1 and G2 are two cographs, then you can also have a Hamiltonian Eulerian cograph such that. So this is a generalized result of the previous one. There is a Hamiltonian and Eulerian cograph such that the median of G becomes G1 and anti-median of G becomes G2. So this is a simultaneous embedding problem. Okay, so I am the problem precisely. What is that? When I have given you one graph and two graphs G1 and G2, then it is possible to find out a new graph with these additional properties as such. This becomes the median and this becomes the anti-median. Okay, so that is what the problem is. The median graph of a planar, okay, connected cograph is one of the following graphs. So it can be K1, K2, K3, K4, K2 bar complement graph. K4 minus C means a graph with an edge is removed. C4, the complete bipartite graph. C4 join K2 bar. Okay, the anti-median graph of a planar connected cograph is one of the following graphs: K1, K2, K3, K4, etc. So which means that if you need any graph other than this collection as a median or anti-median of a planar connected cograph, then it is not possible. Okay, so that is the result says. Okay, now coming to a bipartite graph. So what do you mean by a bipartite graph? Okay, a bipartite graph means you can have a partition of your vertex set such that any edge between the vertices of this graph should be from one partition to the another. Okay, so this is a bipartite graph. So any edge should cross the should be between from one partition to the another partition. So this is a bipartite graph. Now if you can have some k such partitions, then you can see that that is going to be a k-partite graph. Now the first result is that, okay, before that, the importance of this graph class is that it can be seen that the most of the VLSI, that is very large scale interconnection networks, are bipartite. So you can see this particular book in the internet to see these types of claims. In particular, citation networks, recommendation systems in online purchasing, that what we face today, and protein interaction networks, that is the most research area nowadays, and movie actor networks in social networks are all bipartite. Okay, and also most of the analysis in network communities are done using preference networks. That is, this word you can see in this paper and know more about that. and they are modeled using bipartite graphs. So this is what the importance of bipartite graphs and its generalizations. And you can see that any arbitrary graph is some k-party graph. Okay, so any graph is some k-party graph, and the maximum value of k is n, where n is the number of vertices in the graph. Now, moving to one of the result, I think I already have taken maybe more than 1 hour, so I will be stopping in say 10 minutes, or otherwise please mention. So here you have a graph, and I will be showing you how to find out another graph with this graph as the median. Okay, now what is the property that I want to keep? I want to keep the property that the graph should be bipartite. So this is a bipartite graph. Okay, now what I want is a new bipartite graph with this graph as the median. So let this x and y be a partition of this graph. Then you make copies of x and y. So let x dash y dash be the corresponding copy of this x and y. Make a collection, another copy. Then you also make two vertices which I call as the vy and vx. Okay. Then what you have to do is you make vy adjacent to these two copies and make vx adjacent to these two copies. Now if I perform one more step, then we have the final result. Yes, what you have to do is, I have already written the, if the sentences are not clear, please read it here. If you take any particular vertex, for example, let us take this vertex. Okay, then for each vertex in this capital X, make v dash. Okay, so v dash is this vertex, that is the copy of that. You make it adjacent to y minus n of v. So here we know that this is y and n of v is the neighbor set. So this is neighbor set n of v. Okay, and therefore this becomes what or b without n of v. So it is y minus n of v. Okay, then if you do perform like this, and also you make v adjacent to the y minus n of v dash. Okay, that is from this to this, then we get a new graph which I call as the h dash. Okay, so I have performed all these things. Now if you compute the status, now how can you calculate the status? Status is you find out all vertices at a distance 1, or number of vertices at a distance 1 into 1, plus you find out the number of vertices at a distance 2 into 2, then you find out the number of vertices at a distance 3 into 3, and you take the sum of all this. Okay, so here you can see that this n of v is at a distance 1, so this is at a distance 1 from this particular vertex. However, you can see that this will be at a distance 3 from this particular vertex. So I am calculating the status of this vertex to all other vertices. Oh, sorry, I am calculating the distance of this particular vertex to all other vertices, and I am going to calculate the distance from this to neighbor set, means it is 1, and it is already the copy of the neighbor set will be having at a distance 3, and this vertex to the non-neighbor set will be 3, and this vertex to the copy of the non-neighbor set will be 1, and this distance to this particular vertex would be 2. Okay, because this is always adjacent to the neighbor set, and this particular vertex to this will be 1. If it is 1, then it is the all other, that is the x minus 1 vertices will be 2, and if I calculate this vertex from, sorry, the distance from this particular vertex to here, it will be clearly, it will be 2, because this is already adjacent to this, so which means that I can have 2 times x dash. Okay, and 2 times x minus 1, and 1 times 0, and 1 time neighbor set of v, and 3 times neighbor set of v, which together gives you, so these two. Now let me compute all this. So I can have 4 times neighbor set of v and 4 times the non-neighbor set of v. Okay, and if you look like this, then you can have 4 times the copy of x Okay, sorry, maybe 2 times the copy of x, and 2 times the copy of x minus 1, and there are 2 more vertices, then additional 3 vertex is there. Okay, so at to the distance from this to here is 1, 3. If you calculate, you can see that you can perform all this calculation and see that this is 4 times x, oh sorry, 4 times y, and you can have 4 times x together, and which together forms 4 times n, and this, if you subtract 3 minus 2, then you can have some plus 1. Okay, so this is precisely what this result is. Okay, so what I have done is that I have shown that all the vertices have all these vertices have status 4 and plus 1 equal. Okay, now if it is a minimum of this construction, then I can hold this as the median. So for that, I will add an additional embedding. Okay, some K2s, so that this collection will be say green, which means that this forms the median of G, and the other collection, some of the vertices in the other remaining vertices form the anti-median, and so on. So which means that whatever be the graph I have a bipartite, I can construct a new bipartite graph with this graph as the median. Now I will just explain the result, remaining results, because I can conclude in that way. The similar result exists for anti-median structure also, and if you have a k-party graph, then the construction is not very easy. However, it is possible to find out a graph with the prescribed graph as the median, and similarly for the anti-median also. Okay, now you can see that any k colorable graph is the, if using the same result, you can, as a corollary, you can mention that any k colorable graph is the median of a k colorable graph G, and anti-median of a k colorable graph H. Okay. Now you can see that if one vertex is added to any construction, then you can see that the entire construction, the entire status of the all the vertices changes. Now what we can perform is that it is possible to identify or simultaneously embed the median and the center together in a graph. Okay, the exact statement is that given two k-party graphs G and J, okay, then you can have a new graph. So let it be G and J. Then you can have a new graph such that this will be the median and this will be the center. Okay, that is the result that I have mentioned here. Similarly, the same result for anti-median also you can find out, right? Now, yes, there is a concept of symmetric bipartite graphs. Okay, so a bipartite graph is symmetric if for any bipartition of G, if for some bipartition of G, there is a map from X onto Y such that every edge U f of V in G, there is an edge V f of U. Okay, so if this vertex has so and so adjacencies here, then its image, corresponding image, has the mirror images. Okay, then I can say that this is a symmetric bipartite graph. Okay, so it is possible to draw that graph so that this is the mirror reflection of that. Okay, that is another result. Now, so this is a symmetric bipartite graph, and this is not a symmetric bipartite graph. Okay, now you can see that all the previous results that can be extended to the symmetric bipartite graph. For example, given two symmetric bipartite graphs, there exists symmetric bipartite graphs H and G such that one graph form the median and the center, the another graph has the anti-median and the center, the given graphs G and G. Okay. Now, another result is that now I have stopped the finding out the embedding or a graph as the embedded graph, another graph with the median or anti-median or center property. Now we have an operator type. The distance related, another result, distance related problem is that we can operate this median operator with this bipartite graph operator. Okay. That is, okay, before that, let me define what is a bipartite graph. The bipartite graph B of G of a graph G can be constructed as, so given a graph, so this is a graph G, the corresponding bipartite graph is performed like you make a copy of the same collection, okay, and since U and V are adjacent, you delete this edge and perform an adjacency like this. Okay, now since this is an edge, you delete that edge and perform an adjacency like this. And since these two vertices are connected by this edge, you delete that and you can perform adjacencies or make adjacencies like this. Okay, so this is I think everything is over. Now after that, you make adjacencies from a particular vertex to its corresponding copy, right? Now this is what the definition of bipartite graph of G. So given any graph, it is possible to find a bipartite graph corresponding using this operator. Now the result is that this bipartite operator and the median operator commutes. Okay, that is, if you, let us take a graph G and you take a B of G and the median of that M of B of G, and similarly if you start with M of G and B of M of G, then you can see that these are going to be the same. Okay, now similarly the anti-median operator also commutes with the B of G. So using this, we have two new results. It is possible to find out these results. The axis graphs H1 and H1 dash such that median of H1 dash is G dash and center of H1 dash is J dash, where this G dash and J dash are already bipartite graphs of some graphs G and J. Okay, and this, what is the connection between these two is that the H1 dash and G dash are connected using this, yes, H1 dash and H1 are connected using this relation. H1 dash is the bipartite graph of H1. Now, similarly, you can have the result for anti-median also. Okay, so that is how this bipartite graph is related to the median operator. Now, using this, you can see that even though we are using a subclass of graph class, that is not, it is not even a bipartite graph, it is symmetry bipartite graph, and bipartite graph is an operator. Then using this, you can see that the actual problem can also have a solution. This means let G and J be two connected graphs, need not be bipartite, need not be any bipartite graph, and so on. Then it is possible to find a new graph H1 such that the already given, one of the already given graph forms a median of that, and the second graph forms the center of that graph. Okay, or you can find a new graph H2 such that the given graph forms the median, anti-median, and the given graph forms the anti-median. Okay, now that can be done using the combination of these operators. For example, here B and AM are different operators that we have performed. So starting from G, starting from G, you can reach it G dash in this way, right? Now another operator that we have is that the square operator. Okay, so what is G square? So I will show you it in just 1 minute. So you can see that the 1 and 3 are at a distance less than 2, right? Less than or equal to 2. So these are already distance less than or equal to 2. So I have adjacency here, and 1 and 3 are at a distance less than or equal to 2. So means I can make an adjacency. I can make an adjacency from 1 and 3. Similarly, I can have 2 and 4 at adjacency. At a distance less than or equal to 2. Similarly, I can have 1 and 4. Okay, 2 and 5, 5 and 3. So what I have taken is I have taken C5 square. Okay. Now there is a new definition. A subgraph can be called a square subgraph if H square and the graph induced by the vertex set of H and the original graph G square are the same. So in order to clarify that, let me calculate P4 square. Okay. So here how to find out a P4 square? Make all adjacencies, right? Right. Now you can see that this graph is not the induced subgraph here, because we can see that the corresponding induced subgraph with these vertices is actually K4. Okay, so K4 is the induced subgraph obtained by these vertices 1, 2, 3, 4. Okay, so here P4 is not a square subgraph of C5, because we need to have P4 square induced in this graph, so it is not induced. Now the final two results are there. You can do the operator median and square can one by one, so that you can see that they commute each other. If the median of G and the anti-median of G are square subgraphs of G. Okay, that is, the GBA graph says that the number of vertices at all distance from U is a constant from all U in vertex set of G for all in vertex set of G. If M of G and AM of G are square subgraphs of G, then median of G square and the square of the median are the same. Similarly, anti-median of the square of the graph and the square of the anti-median graph are the same. Okay. Now, sorry, I have accidentally go to the end of the slide. Now there is one more problem that I will be quickly solving as early as possible. So means explaining. The last result I want to mention is that on the converse structures. Okay, so what do you mean by a converse structure? In a converse structure, you can see that the shortest distance, or when if you have a graph and you have a collection of collection of vertices in that, and you call it a convex, then the corresponding meaning is that all the shortest path between any two vertices in that graph is in that structure. Okay, so then you can call this as a convex structure, right? So suppose you have another vertex where any shortest between these two vertices are through a vertex outside that, then it is not a convex structure. Okay, now what is the importance of this the convex structure? You can ensure that when we stress on the communications that pass through only the shortest paths between the nodes, then if the underlying or the structure that we have clearly taken out is convex, then you can ensure that all communications are secure, because no communication which passes through or which uses the shortest communication will not go to outside of the structure that we have defined. Okay, so that is the importance of a convex structure. Now there may be a small sound, additional sound, because okay, from the nearby home. So we can see that you can simultaneously embed median and anti-median of two graphs. Sorry, you can simultaneously embed two graphs as the median and anti-median with both as convex subgraphs and also at a preferred distance, prescribed distance. Okay. So I will be using this notation later. So the notation is that the status difference of G, SG of G, is the maximum value of any two. The maximum value is the status difference in that graph. Okay, so you take all the statuses in the graph, then you find the maximum value and minimum value and take the absolute difference between difference. Then that is going to be the status difference. Then we have a result which says that the maximum and the minimum status difference of a graph has these two bounds. Okay. Okay, this is the final result. So this is a result from K. Balakrishnan and John. That is, if given two graphs J and G, it is possible to have another embedding so that this J is median and also convex. Similarly, the G is anti-median and also convex. Okay, and the distance between these two can let it be R. Now there is a maximum limit or limit to these constructions that I am going to mention in the next slide. Sorry. Okay, this is also another result by Dangelman and Sabidosi, that it is possible to have a graph as the median and also convex subgraph of another graph. Yes, this is a condition that they have. That is, if you construct two graphs as the median subgraphs and median, convex subgraphs and median anti-median of another subgraph, then the distance r depends on the diameter of G1 and G2. Okay, so the distance depends, means you cannot make the median and anti-median arbitrarily close to each other. Okay, so that is the result in that. And the final result that we have is that given any two graphs, G1 and G2, okay, sorry. Yes, given any two graphs G1 and G2, it is possible to make this G1 as the median and G2 as the anti-median, and you can have arbitrary distance. Whatever the distance are greater than or equal to 1, you can have a new graph with G1 and G2 as the median subgraphs and G1 as the median and the anti-median, G2 as the anti-median, and distance R is arbitrary. Okay, then we can see that this is the final result. This type of graphs exists for every G1 and G2. Okay, so that is the final result that I want to mention. So there is a lot of noise here, so I am concluding by showing my final slide. This is the final slide. So whatever be the future works that you can perform can be motivated. You can get motivated from these two books. One from Junisu on interconnection networks. So different types of networks that you can see here, and there is a median. You can perform the median center problems on these types of networks, and there are thousands of or hundreds of operators in this book by Eric Prisner that I will see later. I'll show you later, and you can perform the related problems. That is, what are the operators that are communicated with this median and anti-median or even center. Okay, so I have completed my slides. If you have any questions, you can ask it now, and there are a number of references. You may screenshot, or maybe the organizer can make it available to you later. So there are a number of references in connection with these types of results. Okay.
Thank you, sir.
Yes.
Dear participants, if you have any question, please ask.
So I will be giving the that reference slides and everything to the organizers. Okay, so you can see that later. Any questions? Oh, it's 1 o'clock, already 1 o'clock, right?
So we can wind up the session. For the vote of thanks, I invite Diana.
Good afternoon, all. Now it's time to thank our resource person, Dr. Pravas, for his wonderful presentation. Thank you, sir, for that informative class. Now I thank our dear principal for her guidance and support. And I thank our coordinator, Soumya, for her great efforts in organizing this webinar. Thank you all participants for your cooperation. Thank you.